Hello dear students, this is KOUSHIK. In the previous video, we have discussed types of relations. So now we will solve some exercise problems, exercise 1.1. Okay, so first problem. So what is the first problem? Determine whether each of the following relations are reflexive, symmetric and transitive. So determine whether each of the followings are reflexive, symmetric, transitive. Okay, so in that first one, so first problem is the relation R in the set A is equal to 1, 2, 3, 4 up to 14. So the relation is defined by R is equal to the set of all x comma y such that 3x minus y is equal to 0. This is the problem. So problem is determine whether each of the followings are reflexive, symmetric, transitive. So let us recall what is reflexive. A relation R in a set A is said to be reflexive if the ordered pair with itself belongs to R for all A belongs to the set A. Next, symmetric. What is the definition? If A comma B belongs to R, this implies B comma A must belongs to R. Then what is transitive? If A B belongs to R and B C belongs to R, this implies A C is belongs to R. This is reflexive, symmetric and transitive definition. Okay. So first, here I am taking solution. R is equal to what is x comma y such that what is 3x minus y is equal to 0. 3x minus y is equal to 0 means 3x is equal to taking minus y to the right hand, we get y, or y is equal to what? 3x. 3x is equal to y, same as y is equal to 3x. So therefore I am taking here y is equal to 3x. It means the first element is related with second element by means of taking multiplication with 3 to the first element. R is equal to, here x and y belongs to the set A. What is A? 1, 2, 3, 4 up to 14. So now I am taking first element is 1. So what is y? Y is 3x. If I take 1 in place of x, that is 3 ones are 3. Okay. Next, taking second element 2, then we get what? 3 2s are 6. That is in place of y. In place of x, if I take 3, then it becomes what is y? 3 3s are 9. Okay. So next, if I take 4, then what is y? 3 4s are 12. If I take 5, then it becomes 3 5s are 15. But 15 is not in this collection. So we stop up to this. Is it clear? Because the relation R is a mapping from A to A itself. A contains only 14 elements. If here in place of y is belongs to A, so 15 does not belongs to A. Therefore, we stop up to this. If I take 6, then 3 6 are 18. 18 is also not in the set A. So therefore, the relation R, which contains exactly 1, 2, 3, 4 elements, that is 1, 3, 2, 6, 3, 9, 4 and 12. So now let us check for reflexive, symmetric and transitive. First, reflexive. For that, here reflexive, to check reflexive, the element with it itself, is it belongs to R? If I take 1 with 1, is it belongs to the relation R? 1 with 1, 1 with 1, 1 with 1. So does not belongs to R. If I take 2 with 2, is it belongs to the relation R? Check for 2. No. If I take 3, which also does not belongs to R. 4 with 4 does not belongs to R. Up to check for last element, that is 14, 14, which is also does not belongs to R. Therefore, the given relation R is not reflexive. Therefore, not reflexive. Is it okay? A relation is to be reflexive. Take any element, every element of the set A, ordered pair of itself must be in that relation. Then we say that that relation is reflexive. Otherwise, it is not reflexive. Next, symmetric. For symmetric, take any ordered pair whose reverse also belongs to that relation. Then we say that that is symmetric. If I take 1, 3, first element 1, 3 is clearly belongs to R. What about the reverse 3, 1? The reverse of the ordered pair 3, 1. Is it belongs to R? Is it belongs to R 3, 1? No. So there is an element in R but whose reverse order not in the same R. So therefore it is not symmetric. Take another element, namely 2, 6. 2, 6 clearly belongs to R. What about 6, 2? Is it belongs to R 6, 2? Here we have 2, 6. Here we have 3, 9, 4, 12. 6, 2, which does not belongs to R. Therefore, it is not symmetric. Check at least one element for which is not symmetric or it is symmetric. To be symmetric, we check for every element. Okay. For 1, 3, for 2, 6, for 3, 9, for 4, 12. Okay. Next, transitive. Is it the relation, given relation is transitive? To be transitive, the ordered pair AB belongs to R and BC belongs to R means AC also belongs to R. If we have the ordered pair AB, BC, here BB is common, then the ordered pair AC is also belongs to R, then we say that that is transitive. Here I am taking, say, 1, 3. 1, 3 belongs to R and start with what? 1, 3 start with last element 3. So 3 with element 9. So 3 with 9 belongs to R. Means A to B, B to C. So here these two elements should be common. 3, 3 common. So clearly 1, 3 and 3, 9 belongs to R. What about 1, 9? Is it belongs to R? 1, 9 in this relation? So 1, 9 does not belongs to R. It means AB belongs to R and BC belongs to R, but AC does not belongs to R. Therefore, this relation not transitive, not symmetric. So this is an example for which is neither reflexive nor symmetric and nor transitive. Is it okay? Neither means not a reflexive. Neither symmetric means not symmetric. Nor transitive means not a transitive relation. So, dear student, please note down. Here is the from here is the solution. Here the question. So take from this. Note down. Please pause the video and note down the up to this. So this is the definition. Next problem. Second problem. Under the same question, determine whether each of the following are reflexive, symmetric or transitive. So second, okay. Second problem is relation R in the set N of natural number. The relation R in the set N. Here A is N. The relation R in A, that is here set is natural numbers and defined as R is equal to, set of all x comma y such that y is equal to x plus 5 and x must be less than 4. That is the question. So relation R in the set n of natural numbers defined as R is equal to x comma y set that y is equal to x plus 5 and x is less than 4. That is the question. So let us solve this. Whether it is reflexive, check it for whether it is reflexive, symmetric and transitive. Here are the definitions of reflexive, symmetric and transitive. So what is the set? Natural numbers. Natural numbers means counting numbers 1, 2, 3, 4, 5 and so on. Start with 1. So here the relation R is equal to x comma y, where x comma y belongs to the set natural numbers. Here first I am taking 1. What is, if I take in place of x1, what is y? 1 plus 5, 6. Is it okay? If I take 2, then what is y? 2 plus 5, that is 7. If I take 3 in place of x, what is y? That is 3 plus 5. 3 plus 5 is 8. If I take 4, is it? If I take 4, so it is not possible because here is the condition x should be less than 4. It means we must take up to 3, not 4. If they given less than or equal, then we take 4 also. Here they given strictly less than. Therefore, we take in place of x 1, 2, 3. That's it. Okay. So now check for reflexivity, symmetric and transitivity for this relation. First, whether it is reflexive or not. A relation is to be reflexive. The element, take any element of the A whose ordered pair with itself must be in R. That is reflexive definition. Here is reflexive definition. Please note that. I am taking 1. With 1, is it belongs to R? Is it belongs to R? 1, 1, 1, 1, 1, 1. No. So 1, 1 does not belongs to R. If I take 2, is 2, 2 belongs to R? No. 3, 3? No. Therefore, we conclude that check for only one element. You must write only one element. Here, therefore, it is not reflexive. So, which is not reflexive? R is not reflexive. The relation R, that is this one, which is not reflexive. Next, check for symmetric. So, symmetric. First, what do you mean by symmetric relation? If I take any ordered pair whose reverse is also belongs to that relation, I am taking 1, 6. Here 1, 6 belongs to R. If 1, 6 belongs to R, this implies is 6, 1 belongs to R. 1, 6 clearly belongs to R. What about 6, 1? 6, 1 is not in the relation R. Does not belongs to R. If I take 2, 7, here is the 2, 7. Is 7, 2 belongs to R? 2, 7 is belongs to R. What about 7, 2? Does not belongs to R. If I take 3, 8, 8, 3. 3, 8 is belongs to R. What about 8, 3? Does not belongs to R. So therefore, here the given relation is not symmetric. Next, for transitivity. Shall I rub this? Okay. Here I am taking transitive relation. So a relation to be transitive, we must take two ordered pairs AB, BC. Here BB is common. Then we check for whether the relation contains AC. Is it okay? So here I am taking 1, 6 belongs to R. We start with what? 6. Is there any element starting with 6? No, we don't have such pairs. So therefore it is not transitive. So we conclude that there is no such pair such that AB belongs to R and BC belongs to R implies AC belongs to R. So therefore it is not transitive. Take 2, 7. We search for starting with 7. 2, 7 with 7. No, we don't have any number such that start with 7. So therefore we don't have BC. Okay, so which is not transitive. If I take 3, 8, is 8 with some element, is it belongs to the R, such an element? So we don't have such an element starting with 8. Therefore 3, 8 belongs to R, but we don't have such starting with 8. Therefore we conclude that the relation is not transitive. So this example is also not reflexive, not symmetric and not transitive. That is neither reflexive nor symmetric and nor transitive. Is it okay? So take from here solution from here to here. So for transitivity, write one sentence, that is we don't have such pairs such that AB belongs to R and BC belongs to R implies AC belongs to R. We don't have such pairs. So that is conclusion for transitivity. So therefore neither reflexive nor transitive nor symmetric. Please pause the video and write it down. Okay, next, third problem. Under the same question, determine whether each of the following are reflexive, symmetric, transitive. So, next, third problem is relation R in the set A is equal to. The relation R in the set A is equal to, what is A? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. With the relation R is equal to defined as set of all x comma y such that x comma y such that y is divisible by x. Y is divisible by x. That is the question. So first, I am defining what do you mean by divisible. So here, before going to the answer to this question, so what do you mean by divisible? Here, I am taking example 2 divisible or divides 4. 2 divides 4 or A divides B means here this represents A divides B or B is divisible by A. Both are one and the same. A divides B means and B is divisible by A. Both are same. So what it means is A divides B is nothing but B is equal to A into some number. That number belongs to integer. It means I am taking 2 divides 4. Why it divides 4? Because 4 can be here, 4 can be written as 2 into some number. That number must be an integer. So what is that number? 2 ones are 2 but not equal to 4. 2 twos are 4. Therefore that number x is nothing but 2. It is clearly an integer. Okay. So 2 divides 4 or A divides B means B can be written as A into something. That something must be an integer. If I write P divides Q, it means what? Q can be written as P into something, say Y. Okay. Here 3 divides 6. Is 3 divides 6? Yes. 6 can be written as 3 into some value. What that value? 3 2s are 6. So then LHS, RHS both are equal. So where 2 is an integer. Okay. So take any one. So divisible. Here I am taking say 10 divides 2. 10 divides 2 is 10 divides 2. 2 can be written as 10 into some value. That must be an integer. So here we don't have such an integer. If I take 1, 10 ones are 10, not equal. If I take 2, 10 2s are 20, not equal to 2. If I take 1 by 5, 1 by 5 means 5 ones are 5 2s are, then 2 is equal to 2. But 1 by 5, not an integer. What are the integers? 0, 1, 2, 3, minus 1, minus 2, minus 3 and so on. Okay. So 10 does not divide 2 under the integers. But 10 divides 2 under real numbers. Real numbers means it contains all rationals and irrational. Is it clear? Okay. So now I am taking some examples for divisibility. Is 2 divides 2, that is an element divides with itself? Yes. Because 2 can be written as 2 into something. That something must be an integer. What is that? 1. 2 ones are 2. 1 is an integer. Clearly. Okay. So any number divides with itself. 10 divides 10. Okay. 5 divides 5. So any number divides with itself. We can write this. Except 0. 0 divides 0. We can't write 0 divides 0. Which becomes indeterminate form. 1 divides 1. Okay. Next. So this is about divisibility or divisible by or divides, it means. Okay. So here B must be greater than A. So here 4 is greater than 2. If I take 5 divides 10, 10 is greater than 5. So that is divisibility. Next. Is it clear for divisibility? Now we are taking for this we write the Cartesian product with A, 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6. Similarly 2 with 1, 2 with 2, 2 with 3. So okay. First let us check for reflexivity, whether it is reflexive or not. So reflexive means the element with itself, that is A with A. So is it x comma x belongs to R? For all x belongs to A, take any element which divides with itself. Yes, because this belongs to R. Why? This is because to be an element in R, then this element Y must divisible by this element, that is x is divisible by x. So we know that an element is divisible by itself. So if I take any element, 1 divides 1. If I take 2, 2 divides 2. If I take 3, 3 divides 3. Okay. So therefore that pair clearly belongs to R. Take any element. For all x belongs to A. Therefore it is reflexive. Next, symmetric. Is this relation is symmetric? This relation, whether it is symmetric or not. So first, if x comma y belongs to R, we must obtain y comma x belongs to R. What it means x comma y belongs to R means x comma y belongs to R provided y is divisible by x. So y is divisible by x, or it means x divides y. Okay. Next, It means this one is y comma x, the opposite of this, belongs to R. X comma y belongs to R means this one. But what about y comma x? Is it belongs to R? No. Why? If I take 2 comma 4, it means what? 4 is divisible by x. 4 is divisible by 2. In place of y we have 4, in place of x we have 2. So 4 is divisible by 2. Or 2 divides 4. 2 clearly divides 4. Okay. What about opposite? Is it 4 divides 2? Is it 4 divides 2? 2 divides, it can be written as, 2 can be written as 4 into some number. That number must be an integer. Is it okay? No. So here we don't have such number. If I take 1 by 2, then it's possible. So we don't have that number in A. So therefore, 4 does not divides 2. 2 divides 4, but 4 does not divides 2. So y comma x does not belongs to R. If an element is x divides y, then y does not divides x. Okay. So that is, it is not symmetric. Next, for transitivity, whether the relation is transitive or not. Transitive. For that, take if x comma y belongs to R and start with y. Y comma z belongs to R. We must obtain x z is also belongs to R. X y belongs to R means what? X divides y. Okay. Next, x divides y means, this means x divides y means x divides y, which is equal to what? Y can be written as x into something. Something, say yes. Okay. Now I am taking yz. Yz belongs to R means, yz belongs to R means z is divisible by y, or y divides z. It means what? Y divides z. This means z can be written as y into some value, say t. Is it okay? So now we check for is x divides z. So last one, that is check for xz. Is xz belongs to R? Question mark. That is x divides z. To understand why x divides z, that is, if x divides y and y divides z, then x divides what? Z. Here y is common. X divides y, y divides z, then x divides z. Why it is? So there is solution for this. So now I am taking if x divides y. X divides y means what? Y can be written as x into some integer. Say yes. Next, and y divides z means what? Z can be written as y into some integer. Say t. Okay. Now we show that then, after then, we must evaluate y x divides z. So proof for this, y x divides z. So we must get z is equal to x into some value. X into some value, say anything, that must be an integer. So take that. For that claim, we must obtain x divides z. For that, we show that z is equal to x into some value. Say y, or take p. Okay. So for that, consider LHS. LHS is what? Z. So in place of z we have yt. Y into t is equal to, in place of y we have xs. X, yes, into t. That is x into s t. S and t both are integers, product of integers is again an integer. I am taking that integer as p, where p is equal to st, where p is equal to st. So here we have z is equal to x into something, therefore x divides z. So to show that x divides z, z must be equal to x into something. So we have value, therefore x divides z. Is it clear? So therefore the relation, given relation, divisible relation is transitive. Okay. So next problem. Okay, write down this next problem, fourth problem. So what is fourth problem? Relation R in the set. The relation R in the set A is equal to 1, 2, 3, 4, 5, 6 has, the relation R in the set, fourth one, the relation R in the set Z. Here A is the set of all integers. Integers means 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. Okay. So relation here is R is equal to what? Set of all x comma y such that x minus y is an integer. So what is the relation between first element and second element? The difference must be an integer. Then that element must belongs to R. If I have the ordered pair whose difference is, and if it is an integer, then that ordered pair belongs to R. It means if I have 1, 4, what is the difference of 1, 4? 1 minus 4 is minus 3. So minus 3, here is the minus 3. So it is a clearly an integer. So therefore this ordered pair belongs to the relation R. Is it okay? So now let us solve this problem to check for reflexivity, symmetric and transitivity. So first, reflexive. A relation to be reflexive, the ordered pair of element with itself must be in R. Is x comma x belongs to R? So this element belongs to R. What should be the criteria? The difference of those two must be an integer. What is the difference of these two? X minus x is equal to what? 0. Whether 0 is an integer or not? Clearly it is an integer. So 0 is an integer. So take any element x comma x clearly belongs to R. For all x belongs to the set Z. Z is an integer. So therefore this relation is reflexive. Next, symmetric. For that, take if x comma y belongs to R, then we show that y comma x also belongs to R. Is it okay? So what it means? X comma y belongs to R. So x comma y belongs to R only when x minus y is an integer. It implies x comma y belongs to R means x minus y is integer. So x minus y is an integer means y minus x is also an integer. Is it right? For an example, if I take 2 comma 4, 2 minus 4 is what? Minus 2. It is an integer. If I take 4 comma 2, we get what? 4 minus 2. 4 minus 2 is 2. 2 is also an integer. So, x minus y is an integer. It means y minus x is also an integer. If y minus x is an integer, it means what? If x minus y is an integer, then xy belongs to R. If y minus x is an integer, then it means the ordered pair yx belongs to R. It means the ordered pair yx belongs to R. So, x comma y belongs to R. It implies yx is also belongs to R. Therefore, this relation is symmetric. Next, for transitivity. Next, transitive relation. So, For that, take two ordered pairs, namely xy and yz. We must show what is the claim. Xz is also belongs to R. That is our goal or claim. So take these two pairs. So x comma y belongs to R means what? X minus y is an integer. Next, and y comma z belongs to R means what? Y minus z is an integer. So, we show that xz is also belongs to R. We show xz is also belongs to R. What it means? X minus z is also integer. We show that x minus z is also an integer. So, for that, consider x minus z. X minus z, for that, take minus y plus y minus z. I am taking two extra elements, namely minus y plus y. If I cancel, we get the x minus z. Okay. So, here I am add and subtract y. So, what is x minus y? X minus y is an integer. This is integer. Plus, what is y minus z? Y minus z is also an integer. It is also an integer. We know that addition of two integer is again an integer. So, we get x minus z is integer. Why is the addition of integer is integer? If I add 2 plus 4, we get what? 6. 6 is also an integer. Minus 2 plus of minus 4. If we add minus 2 and minus 4, we get what? Minus 2 minus 4 is minus 6. Then also we get an integer. Therefore, addition of two integer is an integer. So, x minus z is an integer means what? X minus z is an integer means what? X comma z belongs to R. So, that is x comma z belongs to R. Is it okay? So, if I take two ordered pair belongs to R, then the first and last element ordered pair, that is x comma y belongs to R, y comma z belongs to R. It implies x comma z is also belongs to the given relation R. Then we say that that relation is transitive. Is it clear? So, this is an example for the relation which is reflexive, symmetric, transitive. Therefore, this relation is called what? Is an example for equivalence relation. So, what is the definition of equivalence relation? Equivalence relation is a relation which is reflexive, symmetric and transitive. Is it clear? Next problem. Let us take problem number 5. Subproblem. Same question. Determine whether each of the following are reflexive, symmetric, transitive. Fifth one. So, what is that fifth one? Relation R in the set A of human beings. A is the set of human beings in a town at a particular time. Okay. So, here town at a particular time given by town means you can take Bangalore, Hassan. Okay. So, set of all human beings in that town at a particular time. That is the set A. What is the relation? Here, the relation R is equal to set of all x comma y such that x and y work at the same place. Work at the same place. So, that is the question. So, what is the relation? X comma y such that x and y work at the same place. Okay. So, let's solve this first. Then, we take second question B. Okay. So, first reflexive. Is it x comma x belongs to R? So, the element x comma x belongs to R. What should be the criteria? X and x work at the same place. X and x work at the same place. A single person work at the same place. It is obvious, is it right? So x comma x clearly belongs to R. That is, he can work in the same place. Next, that is symmetric. What is symmetric? If I take the ordered pair x comma y belongs to the given relation, we show that y comma x must be in R. X comma y belongs to R implies x comma y belongs to R implies x and y work at the same place. X and y work at the same place. X and y work at the same place. It means y and x work at the same place. If Kaushik and Karthik work at the same place, means Karthik, Kaushik also work at the same place. Meaning is same, but the order is different. Here I am taking y first, next x. Y and x work at the same place means what? If x and y work at the same place, then we have xy. If y and x work at the same place, means y comma x belongs to R. So this implies y x belongs to R. So therefore, x comma y belongs to R implies y comma x belongs to R. Therefore, the given relation R is symmetric. Next, transitive. Here I am taking transitive. For transitive relation, we choose two ordered pairs, namely if x and y belongs to R and y and z belongs to R. So we show that x comma z, the ordered pair x comma z belongs to R. It means x and z work at the same place. So it means x and z work at the same place. What do you mean by x comma y belongs to R? X comma y belongs to R means x and y work at the same place. Next, and yz belongs to R. It means what? Yz belongs to R means yz. If I take yz, y and z work at the same place. Y and z work at the same place. So it means here the place, say Hasan. If x and y work at the same place, namely Hasan, x and y. Here y and z work at the same place. Here y is already there. So y and z work at the same place, Hasan. It means x and z also work at the same place. Is it right? So this implies x and z also work at the same place. So x and z work at the same place means x comma z belongs to R. So it means I am taking here x comma z belongs to R. So x comma z belongs to R. So we have x comma y belongs to R and y comma z belongs to R. This implies x comma z belongs to R. So it means R is transitive. Is it okay? So this is about reflexive, symmetric, transitive for this relation. So it clearly satisfies all the three, reflexive, symmetric as well as transitive. So next, take for B. So please pause the video and take it down. Next, B. Now I am taking B. So what is B? So B is equal to A is the set of all human beings in a town. So R is equal to what is the question number B? B is equal to, sorry, here R is equal to x comma y such that x and y lie in the same locality. So which is similar to the first one as A.